All right. Hello, Nullcon. It's really great being here today, and welcome to my talk, The Invasion of Bad Drivers. So today we'll talk about the not so glorious kernel drivers that exist out there. And for those of you who already managed to recognize the theme of the presentation, it's about chicken invaders. So it's one of my favorite computer games that I used to play when I was younger. But today we are not here to talk about computer games. Kind of. We are here to talk about kernel drivers. So let's begin. So my name is Omer Tsarfati. I'm a senior security researcher at CyberArk Labs. I'm doing security research for about 8 years, maybe a little bit more than that. In my spare time, I like playing basketball. When I'm not doing that, you might probably find me playing some computer games, maybe Chicken Invaders, maybe Call of Duty. You can never know. Alright, so what we're gonna have today. So at the beginning, we will do a quick review of the Windows driver framework. Right after that, we'll talk about some common mistakes that driver developers tend to make. And then we'll talk about one specific driver that created a really big mess. And it's for weird reason, really widely in use. Right after that, we'll talk about aggregation, how we managed to utilize VirusTotal for finding even more vulnerabilities. And then at the end, we'll talk about mitigations, how some of the vulnerabilities we found could be mitigated with one simple trick. All right, so let's begin. Before we'll talk about the Windows driver framework, I'm going to tell you a story. So a few years ago, I made a decision. Maybe not the best decision that I ever made, but a decision. And I went to the store and bought myself a gaming laptop. So this laptop over here, so this one is manufactured by MSI. And as a gamer, and some of you also gamers, you should know that when you play video games, it's not about the graphics, it's not about the engine, it's only about how much frame per second you can get, or FPS. So basically, as much FPS you can get, the better gaming experience you will have. So FPS can be achieved by a lot of ways. One excellent one is by having a good cooling system in your rig. Unfortunately, gaming laptops tend to suffer from overheating because they don't really have a lot of space to put some good cooling systems. So you can do that. You can actually set your cooling fans to the max, or just add a nice spoiler to your gaming rig. It might also work. I don't know, I didn't try. Alright. So MSI was nice enough to create a nice program called Dragon Center, which allows us to control the cooling fans and other stuff on the system. But there is one thing that I personally don't like about this program. I don't like its GUI. So I decided to create my own program that controls the cooling fans. And at this point, before I started doing that, I was thinking about how does the Dragon Center program communicate or at least control the cooling fans. So it must be by using some kind of a driver. So the user space process, the Dragon Center interacts with the driver, right? So before we're talking about user space processes that interact with driver, we need at first understand the Windows privilege level architecture. So there are four different levels of privilege, four different privilege levels in Windows. So you got the lowest one, which is the sandbox processes, which not that many processes runs in at. So basically it will be your browser, Teams, Slack, stuff like this, stuff that you don't want whenever they got compromised, that your machine will get compromised. Then we have the non-admin processes and the service admin processes. So basically most of your processes in the system will run as non-admin processes, and some of your processes on the system will run as admin processes or services. And if those got compromised, so basically the whole system got compromised in a way. So those considered to be privileged. And then we got the kernel and the kernel drivers. So basically, the kernel drivers might be the one that interact with the cooling fans. So the process will interact with this driver. All right. So basically, before we are trying to develop a kernel driver, there are a lot to consider because there is a lot of responsibility when we're doing so. Because kernel driver is actually part of the kernel, of course. So it's an extension for the Windows kernel or any other kernel. If it will be Linux, it will be kernel module. Mac OS, it will be kernel extension. You basically share the same system address space as the kernel, and you're part of the kernel. At least, well, I think most of the modern operation systems, but specifically Windows, won't let you load an unsigned kernel driver as a mitigation. You can disable it. Don't do that. You need to be admin, and at least that kind of eliminate some of the risk when we're talking about kernel drivers. And remember, there is a responsibility. You're talking to hardware devices, you filtering stuff, and please handle exception correctly, because if you won't, you actually crash the system, so there will be a blue screen, BSOD. Right. So we are not here to talk about responsibilities, right? We're security researchers. We're here to talk about how we crash stuff. So when reviewing kernel drivers from security perspective, we should ask ourselves the following questions. So, do I have access to the kernel driver? What are my permissions to talk with it, and how do I talk with it? And another question we should ask ourselves: how does the driver parse the data we send to it? Right. Right. So let's talk about access. So basically, in Windows, in order to interact with the driver, you do it by using a device object that the drivers needs to create. So the driver creates a device object and should specify which user can access it. This can be done by using a security descriptor or SDDL string that could be found either in the INF companion file or in the driver itself when it calls to IO create device secure. So as you already understand, there is also a function called IO create device. That's it, not secured. And this means that the device will be created with a default security descriptor, which basically means most of the users, most of the processes on the system can interact with it. All right, so in order to make the device object accessible from other processes and specifically the user space, so we'll need to create a symbolic link that will be connected to the device. So you can do it by using IO create symbolic link or IO register device interface. And so the client will actually use create file or anti-create file to the symbolic link that created in order to get a handle and from there to interact with the device. So here we can see a driver called vidsys exposing a device object called videxo. You probably can't see anything, so let's zoom in. So on the left-hand side, we can see a driver object and all the devices it exposes to the object manager, and then facts. On the right-hand side, you will see groups and the users that have access to the device and what is their access to it. All right, so let's talk about a little bit about communication. So basically, the driver needs to register dispatch routines by using the driver object measure function, and there are about 27 different routines that the driver can actually register. Most of them are not really in use. They are not commonly in use, at least, and the most common ones are create, close, write, read, and device control, or device I control, or file control device, which most of them share the same idea, purpose, let's say. So this is how a typical driver function looks like. So here we can see there is the IO create device call. So this is where the device will be created, called testy driver. And after that, there is a registration of a major function and the most important one, which is the device control dispatch routine. So basically, the device control routine is the main interface we users or researchers have with the driver, and where the most interesting logic exists in. So at least for our needs. All right. So whenever we communicate with the device, we will send a packet, just like whenever a computer talks with send a packet to another computer. So you will have TCP packet. You will have not a network packet. You will have IO request packet, or IRP for short. And IRP is actually a struct that has everything, all the parameters, everything that the IO. Alright, so the IOP structure is generated by the IO manager, and it consists of stack location where all the important members are residing. The requester mode, we initiate this call to the driver if it was the kernel, if it was a user mode of the process, the input and the output buffers that send to the driver, and the IO status information, which indicates how many bytes should be written back to the output buffer. Any misuse of those fields will probably cause a bug. Right. Besides that, the IOP struct contains a IO control code, or IOCTL for short. So the IOCTL number is just a number used as an identifier for other programs to execute specific logic in the driver. So the IOCTL is just a function identifier, right? Well, we are not talking about Linux here, so it's packing much more than that. So in Linux, you should actually, maybe, I don't know, consider handling the IOCTL properly. Here you must do it because the IOCTL packing a little bit more than that. So basically, it's a 32 packed structure that the first 2 bits indicate the transfer type of the request that is sent, and the 13 and the 14 indicates the required access of the request. So let's talk about the required access. So those 2-bit number describes the required permission to send the device IO control request. It's based on the permission you used in the call to empty create file. So there are 4 different options: file any access, file read access, file write access, and file read access and write access. So those are in order from the least privileged one to the most privileged one. So if you got read access and write access, you can perform some actions that mostly restricted users won't be able to do. And there is the transfer type, which is actually describe how the IO manager treats the user data. So there are many nonsense that the driver developer must know here. And as you know, when there are many nonsense, there are many bugs. And this caused a lot of bugs, and we'll talk about those later on. So there are here also 4 different options. So there is method buffered, method indirect, outdirect, and method neither. And as before, this one also in order, but from the most secured one to the least secured one, which means if you use method neither and not doing some stuff we'll talk later on, probing and stuff, you will actually have some serious vulnerabilities in your driver. All right. So in order to send device control requests, we'll use a function called device IO control. The device IO control takes the following. So it takes handle to the device, takes the IO control code, the input buffer in its length, and the output buffer in its length. And that's what you should know by now. So right now, we know how to interact with some of the driver in Windows. So we can talk about mistakes. So let's talk about some common mistakes that driver developers tend to do. Let's talk about method neither, or as some of my colleagues call it, mother of all evil. So the 2 bits are on, the IOCTL number ends with 2 bits 1, 1. The IO manager in this case is actually lazy. The buffers and its length reside in the user mode. The kernel doesn't copy any of them to the kernel space, and those can be paged out. The input and the output buffers so the input buffer will be type 3 input buffer, part of the current stack location, and the output buffer will be user buffer. So the user can allocate and deallocate the buffers, making them those pages invalid, and you must be cautious when you're handling with them. And remember, every interaction with those buffers should be in a try except block. And you should also do some probing. So probing actually validates that the addresses reside in user mode. As I told you, the IO manager doesn't do anything here. It just passes the pointers to the driver. So whenever you want to do a read operation or write operation, you should call probe for read and probe for write accordingly. But if you don't probe or you don't use the function correctly, then the function might throw an exception, and if you're not handling the exception, you will crash the system, so you'll get a BSOD. And if the length is 0, or the buffer size is 0, so it just passes the validation without any probing. And this also could lead some bugs. So if not probe and the kernel reads from it, you will get at the lowercase BSOD and the better case for security researchers at least an info leak. If not probe correctly for write, you will get a BSOD or arbitrary kernel memory write. This is really bad. Let's see an example. So here we can see in this snippet at least 4 different bags. So at the beginning, there is so at the first box, we can see that the driver reads the input buffer. We can see there is no probe function before the usage. In the second one, we can see that the driver developers dereference the pointer without checking if the buffer is null. And on the third box, the address could already be paged out, causing a crash when writing to the output buffer. Besides that, the input and the output buffer are accessed not in a try-catch block, so the driver can get access denied and crash the system. And also, just like in the second box, in the fourth box, we can see the driver developers accessing an input buffer without any validation. And lastly, any access to so they don't actually do any probe for probing on the output buffers, so you can actually achieve arbitrary kernel write whenever this buffer gets written, and this is bad. Alright, let's talk about the better brother in the family. Let's talk about the method buffered. So the 2 bits will be off, so the IO octal will ends with 2-0. In method buffer, the IO manager actually copies the buffer to the kernel and in a secure manner, so you won't get the same faults as before. In this case, you don't need to do any probing, and the buffer but you do need to do some validations if the buffer you are sending to the driver embed some fields or members or pointers, and you do need to treat them properly. So in this case, the input buffer and output buffer will be in the same member, so it will be system buffer. One thing you should know, that the IO status information indicates how many bytes will be copied out to the output buffer. We talked about this before, but if the IO status information is bigger than the input buffer length and the output buffer length is bigger than the input buffer length, you actually get yourself some memory leak. Why is that? Because so basically the IO manager would just copy as many bytes that you will ask for, and this actually can lead for a really huge info leak. Let's say if the output buffer is 1000x and the input buffer length is 8x and the IO information status is equals to the output buffer length, you will leakage about a page size of kernel memory to the user mode. So this is bad. Don't do that. And here is an example for exactly this, and even worse than that. So here we can see a switch case that handling IO buffer IO octal. So again, even if they're using method buffered, it's not safe to assume there is going to be bug free, even if it's the better brother in the family. So on the second box, we can see a nice length check, and beneath the check, we can see there is some logic. And if this one fails, so there is assignment to the IO status information, which a really huge number, which means we will leak 11K of the kernel memory to the user space. This is not good. So all those examples are really taken from real drivers that we did the research on. So yeah, it exists out there. This is bad. Let's talk about direct IO. So we got 2 here. We got method indirect and method outdirect. So in this case, we will have 2 buffers. So we will have the system buffer as in method buffered, and we will have another one called MDL address. So the second buffer is a direct buffer, which always be paged in. So it will be faster to access. The buffer can be used for input and output. And also the kernel driver can create an MDL with IO create MDL, followed by locking with probe and lock pages, which would throw an exception if the page is invalid. Right, so what is MDL? So MDL is a structure that describes a fixed physical memory location that comprises a contiguous data buffer in virtual memory. Or in simple words, the MDL describes the data buffer at a fixed position in the physical memory, which will always be paged in and locked in the memory. So it's basically double mapping, one for the user and one for the kernel. Alright, so in this case, we can see a bug. We can actually control the controllable virtual address variable, and we can actually make the page that this virtual address to be invalid. And whenever mmprobe and lock pages will be called, it will actually throw an exception. And because this call is not wrapped with try catch block, we will actually get a BSOD. So we will crash the system. All right. So we talked a lot about vulnerabilities and I gave some examples. So let's talk about one specific. Let's get back to my laptop. So I tried to find out how the Dragon Center interacts with the driver, and I found out that there is a driver that it's been loaded by Dragon Center program, which called WinIO. And this, so I checked if I have access to the device object it exposes, and fortunately, I do have access to interact with it. So I open IDA, which is my favorite disassembler, don't blame me, and don't judge me. And I started to do some reverse engineering. So basically, I decompiled some of its code and went into the dispatch routine. Here we can see that the driver takes the system buffer and that is been sent to the driver by the user, and then we can see there is a nice handling of the different major functions. And whenever it comes to dispatch to the device IO control, we can see there is so the driver takes the ioctl out from the current stack location. And for those of you who are really sharp, we can see in line 47 something really weird. So here we can see a memmove to a local variable that takes the system buffer, the buffer we fully controlled, and the input buffer length, which we also fully control, and copies it to a local variable. Yeah, this is not good. So basically we have a potential stack overflow here. And so it means if we will override 38x plus 8 for the return address, we might be able to achieve kernel execution. And when we will send this request by using device IO control, we'll get kernel BSODs, and we actually managed to override RIP, which is the instruction pointer. And at this point, you should ask yourself, hold on, isn't there a stack canary that would prevent this? Well, they didn't compile this driver with stack canary. It's something really weird. Like a lot of drivers just doesn't come with stack canary. Alright, so, and don't worry, this is not the only bug that exists in this driver. So you got also arbitrary IO port read and write. That will let us to interact with hardware components from a restricted user, from a low privileged user. And there are also mapping and unmapping of physical memory to virtual addresses upon a request. So it means we can actually write to whatever physical memory we would like. And this is also a big problem. Right. So there is a lot of process here, but wait, there is more. As I told you before, as a gamer, I want to get as much FPS as I can get in games. And only real gamers know that RGB gives you FPS, right? So basically you can achieve RGB in various ways. One of those is by buying Razer mag holder. I don't know about that. So after figuring this out, I made another good decision, as you can already understand, and I bought myself a keyboard, a gaming keyboard with a lot of RGB in it. So Razer was nice enough to create a program called Synapse, which let us control the RGB lights on this keyboard. And of course, as a good gaming program, it has also its own drivers. So one driver has been loaded by a Synapse service, which called R0 Razer Synapse service, which also exposes a device object called WinRing0. So just like before, I located the driver file and started doing some reverse engineering on it. So we again went to the dispatch routine, went to the main logic where the device control function is at. Right. So here we can see some, got this? Yeah. Right. So here we can see that this time the driver developers do perform some checks on the buffer, so there won't be any buffer overflows here. Yet there is still the IO port read and write primitives, so we can actually abuse this one. And also we got this section. So this one is actually pretty interesting because the driver let us, as a low privileged user, to write and read from any MSR we wish. At this point, you're probably asking yourself, what is MSRs, right? All right. So let me answer that for you. So MSR, or model specific register, is any various of control registers in the x86 instruction set used for debugging, program execution tracing, computer performance monitoring, toggling certain CPU features, and there is MSR called IA32L star, which holds the pointer to the system call handler, which upon syscalls, this pointer will be loaded into RIP in a kernel context. So basically, if we manage to override this MSR, we will manage to get arbitrary execution in the kernel. All right, cool, right? We didn't check one thing that I told you to do before. We didn't check if we do have access to the device object, right? Just jump into the code. So I went to the driver entry and I look at the IO create device, which is the not secured version of IO device secure. And so there won't be any security descriptor other than the default that will be applied here. So basically we got here a privilege escalation confirmed, right? Almost. So basically, whenever I opened the properties of the device object, I found out that only administrators and system could interact with it. And this is really strange because we see a clear inconsistent between the driver code and the device security object. So the driver doesn't enforce any security descriptor over the device object. It doesn't come with INF file. And the only logical explanation to this phenomena is that some other process changes the security descriptor of the device object. So basically the flow will look something like this. So WinRing0, the driver gets loaded. WinRing0 creates a device object with the default security descriptor, something, and some random process just changed the device security descriptor. Cool. But we can see some time gap between the creation of the device object and the time of the new security descriptor that is applied. So basically, in this time, we could abuse this, and as a low privilege process, we can open a handle to the device object. And in Windows, whenever you got an handle, you win. So basically, it doesn't matter if anyone will change the properties of the device, of the file. You got an handle, you're good. This is true, so you will be able to win this race as long as the driver isn't get loaded before we can run any code and the random process changes the security descriptor before we get a chance to run any code. So we dig a little bit in and we found out there is a service called Razer Synapse service, which uses an open source library called Libra Hardware Monitor Lib, which actually loads the WinRing0 driver. And the WinRing0 driver creates a device with the default security descriptor. We got the race condition there, and some random process changes the device security descriptor. So we looked at the Libra Hardware Monitor Lib, as it's an open source, so we dig into the code. Here we can see, so it creates handle to the service manager and then creates a new service or just creates a new driver. So this is how you actually create a new driver in Windows. And right after that, we can see that the service starts the driver, and after the driver gets loaded, so this library tries to modify the security descriptor of the device object that got created. Alright, that's cool. But unfortunately, this service runs way before we could run any code. So this is a problem. We cannot actually win the race here. Is that right? So we looked for ways to bypass this. We thought like we can win this whenever the Synapse program get installed, but I don't like this approach because it's too narrow. We could not really abuse this vulnerability upon request. But we thought about, what about updates, right? So whenever an update gets triggered, so everything shuts down, replaced, and then starts again. So we'll be managed to create this race condition. But updates, well, you might not be able to run an update because it might require privileges, and you cannot uninstall. But there is one thing you can do, and it's installing. So here we got the race condition, but it's installing. It's installing plugins. So basically, Razer Synapse allows you to install plugins, and for some reason, as a low privilege user, you can trigger it, and it will be considered as an update. So basically, the service that controls everything, the GMS, will shut everything down, install the update, and then turns everything on. So by abusing this mechanism, we can actually trigger the race condition upon request. Another funny thing here is that in the open source code there is a to-do which says replace with a call to IO create device secure in the driver. So yeah, this to-do left behind and nobody really treated this or handled this. Yeah. All right. So this is actually what we did. So we exploited this mechanism. So we created POC exe that asks Razer service to install a plugin. The GMS initiate an update like scenario. WinRing 0 gets unloaded, and then WinRing 0 gets loaded after the update is installed properly, and it creates a device object with default security descriptor. We got a race condition, and we can actually win this. So let's see a demo. So here we got the Razer program. Yeah. All right. So we will just install an arbitrary plugin, for example, Alexa plugin, but we won't do it via the GUI because so we run as a low privilege user. Hope you can see anything. So basically we run as just a low privilege user. We download in the Alexa plugin. Then we will tell GMS to install the plugin. We will abuse the race condition, we will override the IA32 L-star MSR, and from there we will get the kernel code execution, which will help us to change our process token to anti-authority system. All right, so this is done. We run OMI, we are system, and we got all the privileges in the world. Thank you. All right, so let's talk about aggregation. So we found out that the driver that MSI uses and the driver that Razer uses, so it's really similar to one another with small changes. So basically, they use the same code base. So we thought that we might use VirusTotal to find more drivers like this. So usually VirusTotal is used to hunt malwares, but we thought that we will find more vulnerable drivers by using VirusTotal. So we wrote a simple retrohunt job query to include, we included some debug strings from the driver, and we found 114 different drivers that is being used by too many different vendors in their products, and this is really bad. So we're talking about ASRock, MSI, Razer, Asus, Patriot Memory, Galex, Gigabyte, and much more. Yeah, so VirusTotal can actually be used also for finding vulnerabilities, so this is really cool. Let's talk about mitigations. So interestingly, just by having Hyper-V enabled, we can mitigate some of the security risks embedded in WinIO kernel driver. So hypervisors, by design, can intercept any modification action initiated by the OS kernel. So Hyper-V, by default, prevents any modification to IA32 L-star because it doesn't make sense that you would like to change it after a boot. So yeah, makes sense. Unfortunately, the other security issues remain a risk, and and those cannot be mitigated by Hyper-V because Hyper-V can do that much. I mean, right. So is the problem fixed? Sadly, only partially. So the kernel driver is still being used by different vendors. What can I do? So as an end user, just enable Hyper-V in your system and use a proper antivirus that blocks malicious drivers, because those tend to be loaded with malwares. So you can use one. As a developer, just don't use the WinIO codebase, and neither any of the different variation of it. So it will be WinGen0, Anti-Lib, MSIO64, and etc. And if you do use it, please fix the security issues embedded in it. So we got some CVEs. We published a blog post as well. And that's it for today.
Questions?
Thank you. Very interesting talk. One remark, and I might be mistaken here, but as far as I remember, PatchGuard also throws a BSOD if you change the IA32 L-star MSR. Did you guys see any of that at all?
I cannot recall any action that PatchGuard did upon our modification, so I don't really know. I didn't research PatchGuard, so I don't want to answer.
Does it appear in periodically basis?
Yeah. But
it happens after like whatever triggers it.
From what I saw and encountered, that it didn't happen. So I don't know.
Interesting. Thank you.
No more questions? Okay, thank you.
Thanks.